you all for coming here. It's such an honor to be here. And I'm really, really excited to talk to you guys about real time analytics with change data capture. Uh, Today, we have a couple of stuff to go through, and I guess I can just start with the agenda. So, we're going to kick off the conversation here today with a bit of a background on change data capture and some of the problems it solves. Then we'll move on to introduce the different components of a typical change data capture pipeline. And I'll wrap up my presentation with a demo pipeline just to show you how change data capture actually works in real life. But personally, when I do a talk like this, I like to just introduce myself because I feel like it gives the audience some context on my background and it helps to just see my perspective during the presentation. So yeah, I am Clement. I work as a developer advocate at 84 Codes, and I've been in that role for almost 2 years now. And I spend every day working with RabbitMQ, testing it, writing about it, and speaking about it at conferences as well. And before 84 Codes, I'd worked as a full-time Python developer, and I've worked on a couple of open source Python projects as well. One project I'm super proud of is the Django REST CLI. It's on my GitHub. I think it has over 100 GitHub stars now. I've also worked on Django REST PStack. That just helps you integrate PStack into your Django projects more conveniently. And I came all the way from Abuja today just to talk to you. Yeah, and because Abuja is really cold and with lots of snow, I spend my free time. I spend my free time in Abuja skiing or snowmobiling. Is anybody here from Abuja? I just need to confirm that I'm not lying. I'm not lying, right? Anyway, I'm just kidding. My Nigerian story is nothing like that. I, s- I work from home, so I'm mostly indoors. But every now and then, I try to hang out with friends and try out new stuff. And that's it about me. Like I said, we're going to talk about change data capture today. Uh, and personally, when I present like a new technique to an audience, I just don't like jumping into some formal definition, right? I like to first of all paint a picture of the problem that the technique solves. So I'd like you to imagine this scenario. Imagine you're working on some back end logic, right? That writes data to some transactional database, like Postgres, for example. But then here's the thing you need the data in your Postgres in three other places. Let's say you need it in your data warehouse for real-time analytics. You also need that data in your search database like Elasticsearch for quick searching. And lastly, you also need that data in your stream processor. Let's say your stream processor would do something like update some analytics dashboard in real time. Now I repeat because I'm going to ask you a question. You have a data in your database and you want to replicate it in three other places. Just think about it. How would you go about something like this? How would you go about replicating this data? I'll just give you a couple of seconds to think. Does anyone wants to share their thoughts with me on how they'll go about this? There's no right or wrong answer. I just want to hear your thoughts. Yeah.
So there was reference about, sorry, yesterday it was reverse ETL was referenced. Like I don't know if anyone was around for and they mentioned something about reverse ETL where you get the data from the source, take it to the target, and use the target as a source to transfer as to
Mm-hmm.
another
Mm-hmm.
source.
Yeah.
So that works somehow.
Anybody else?
So I'm aware the database of my choice, Postgres, has a has something I'll call pub sub.
Sorry?
Uh, has something I'll call pub sub.
Okay.
Yeah, and I used it recently, and it works well. Yeah.
Yeah. So just the pops up, do you send data from your Postgres directly to the destination?
So we're talking of change data capture. So it's specifically, it's
Or
not for all the tables, but
yeah,
for what I'm monitoring.
yeah,
As soon as it comes in, it notifies, and then I can pick it up from there.
yeah. Okay. I, yeah, I think I'll just work with these answers I've gotten so far. Someone said something about ETL, and I think it stands for reverse ETL, but I'm not super familiar with that technique, but I think generally it's an extract, transform, you load data, right? Um, it falls within the next approach I'm going to talk about. Traditionally, most people move data via batch replication, right? If you're not super familiar with batch replication, what it means is you have some data source and you have some logic that runs periodically, let's say every hour, every 24 hours, or every 3 days. It looks at the data source, it copies your data, replicates it in the destination, right? And it just repeats the process. Now, this is how most people traditionally have been migrating data, and it works really well, but it has its limitations. I'll tell you what these limitations are. Now, with batch replication, you're going to run into latency issues. And what I mean by this is there's going to be a delay between when data is written to your database and when it is replicated in your downstream processes. Now, this might not be a problem in some scenarios, but it is a big problem in real-time analytics scenarios because you want data replicated in real time, right? And second limitation is it is resource intensive, really, because then you're looking at this huge chunk of data that you want to copy at once. Now, you could have, let's say, tens or hundreds of data sources you want to replicate data in. This could put a strain on your server's CPU or memory. As computer people, as engineers generally, what we do mostly revolves around trying to make our experiences, and generally human experiences, actually more convenient, right? So in a bid to find like a workaround the limitations of batch replication, engineers began to adopt a new technique, dual writing. Now, with dual writing, it is self-explanatory, I guess. It's when you try to write the same data to multiple places at the same time. So in the example I gave, you want your data in the database, in the data warehouse, in Elasticsearch, and then your stream processor, right? With dual writing, you write some logic that writes data to Postgres, then writes that data to your downstream processes at the same time, or basically something like this. Now, dual writing sort of helps, and I say that because it's a workaround the latency issue you had with batch replication, because you write to Postgres and you write to your downstream processes simultaneously. So you get the data replicated in real time or near real time at least. And then you don't really run into this resource intensiveness that you had with batch replication, right? Because you're just copying one data at a time as it happens. Now, dual writing might sound really great in theory because you get data replicated in real time. It is not very resource intensive, but even this technique is flawed, incredibly, actually, I believe. Because with dual writing, you're going to run into consistency issues. And what I mean by that is, I'll give you an example, actually, consistency issues with dual writing. Imagine you write data to your Postgres database, and then you want to replicate that data in Elasticsearch, for example, but then Elasticsearch is unavailable for some reason, right? You're going to end up with the data that is in your Postgres database, but then is not in Elasticsearch. You're going to have divergent data sources, right? And relatively, dual writing is a bit more complex because then you have to write logic that writes data to multiple places, and you have to think about like errors and stuff like that. And I would even make the argument that it has slightly more performance overhead. Writing to databases, as we already know, is slow already. But then now you have to write to multiple data sources, right? Um, Now, I've been speaking about the problem. What is the way forward, really? Is there a way to replicate data in a way that's in real time without the performance and resource overhead of batch replication? and dual writing, well, I present to you change data capture. Now, change data capture became popular really as an alternative to batch replication and dual writing. Um, it is a way to automatically capture changes in a database and then stream these changes to your downstream components in real time. And in our case, the downstream components are the data warehouse, Elasticsearch, and then the stream processor. With change data capture, we eliminate most, if not all, the limitations we've seen with batch replication and then dual writing. I'll talk about this a bit more. With change data capture, you don't really run into these latency issues you had with batch replication, because like I said, with change data capture, you capture the changes in real time and you just stream it down to downstream components. Each change as it happens. So let's say you update a record, you delete a record, you insert a record. Change data capture will capture each change and replicate it in your downstream components. I would even say it's a lot more simpler because you just write data to your database, and change data capture would take care of replicating these changes. Most times you don't really have to write any code yourself because there are a couple of change data capture tools that you could just integrate into your stack and work with it. And you don't really get to experience these consistency issues that I talked about when working with dual writing as well. And that's because key component of change data capture is when you capture a change, you don't replicate it in the downstream component directly. What you do is you send that change to some messaging infrastructure or streaming platform. Your downstream components will then subscribe to the streaming platforms and receive these changes as they come. Now, the beauty of this is it is a lot more decoupled. So if, let's say, Elasticsearch is unavailable when a new change arrives, that change will always be in the messaging infrastructure. It will be persisted there, and Elasticsearch could just consume that change when it is back online. Now, I did mention a couple of terms that I think is worth reflecting on and diving deep into. I talked about change data capture mechanism. I talked about streaming platforms. So let's take our exploration a bit further and talk about the different components of a change data capture. Now, one of the key components of a change data capture pipeline is the change data capture mechanism. Now, this is the component that is responsible for capturing changes in the database. Now, the next component is the streaming platform or messaging infrastructure. So when a change data capture mechanism captures the changes, it sends it to the streaming platform or messaging infrastructure. Then the last component is the downstream components, one or more downstream components. The downstream component. Yes, so the downstream components will receive changes from the streaming platform as they arrive. Now, a good change data capture pipeline must have these four components. Some upstream data source, like a database or an application with a database, a change data capture mechanism that captures changes from this database, then a streaming platform where these changes are sent to, and then a downstream component that finally consumes these changes. Yes, like I said, to actually help you see change data capture in action, I'm going to run a demo pipeline. But first of all, I'd like to just kind of describe what our demo pipeline will be about, like what it does, for example. So our demo pipeline is going to simulate like an e-commerce platform's backend that is built the microservice way. So our e-commerce platform would have two services. Of course, in reality, you're going to have a lot more services. But just for the sake of this demo, it would have an inventory service. And then how this would work, an inventory service and an order processing service. So how our pipeline would work is this. When we launch the inventory service, the inventory service has its own database, a Postgres database. So when we launch the inventory service, which we're going to do, it will insert a product into our database every 5 seconds. This is just to simulate adding new products in your inventory. Each product in the database will be added to a product table, and each product would have the following fields: an ID, a name, and quantity. And of course, we've not forgotten about the second service, the order processing service. It will be responsible for processing an order. And of course, in reality, to process an order, you need to check the availability of that product. So basically, our order processing service would need data from the inventory service. Uh, if you've worked on something like this, you're probably aware that one way to approach this is to have the order service create a local copy of the data it needs from the inventory service. If you get what I mean. So basically, the order service would have its own Postgres database, and it will have a copy of the data it needs in the inventory service. Now, for the sake of this demo, I'm not going to go through all that. The inventory service will have its own database, but the order service would not have its database. However, we're going to stream changes from inventory service, send it to the order service. And if our pipeline works, the order service should log these changes to the console in the terminal. We should see it in the console. And now that we understand what the pipeline we want to work with, I just wanted to show like a picture of the different components. Recall we said that a typical change data capture pipeline should have 4 components: some upstream database, data source, a CDC mechanism, a streaming platform, and some downstream components. In our case, the upstream component is the inventory service. The downstream component is the order processing service. But what about the CDC mechanism and the streaming platform? For our CDC mechanism, we're going to use a tool called Debezium. Debezium server, actually. Now, what is Debezium? From the documentation, I just got this definition from there. It says it's a ready-to-use application that streams change events from various source databases to messaging infrastructures. Let me try to help you break this down for you. Let's assume you decide you're not going to use Debezium. You want to write your own custom change data capture solution, right? And ideally, your solution should look at changes coming into Postgres and capture these changes. One way you could do this is to write a logic that hooks into Postgres has transaction logs. If you've worked with it, a database would have like a transaction log. So one way you could go around this is to have some Python scripts that hooks into your database's transaction log, and it reads every change that is recorded in the transaction log, and it sends it to your downstream component. Now, here is the problem. The way you're going to do this would be different for how you do it for MongoDB, how you do it for MySQL, how you do it for Cassandra. So the point I'm trying to make is the approach would vary across databases. So do you want to keep writing logic for every database you want to implement change data capture for? This is exactly what Debezium does for you. It just provides this unified interface that you could use to extract data from a variety of databases. And Debezium does this through what it calls connectors. It has a set of source connectors. A connector is basically a component that is responsible for extracting data. So it has a source connectors for most of the popular databases you could think of. It also has sync connectors, and sync connectors are responsible for extracting data out of Debezium down to the downstream components. And for our streaming platform in the pipeline, we're going to use RabbitMQ. And so basically, we just need to tell Debezium to use the Postgres source connector and the RabbitMQ or sync connector. Yes. So I'm going to try to run our pipeline. So yeah, like I said, the upstream component is going to be our inventory service, right? And it should insert new product into our database every 5 seconds. So I'm going to run the inventory service. I have my terminal here. So I package my services in Docker because I'd written a blog about this and I wanted people that are non-Python developers to be able to follow it as well. So yeah. I'm going to run my Docker container for the inventory service. I hope my internet works. It should work now. Okay. So how do we know that our inventory service is adding data to our database? I have PG admin here just to get an idea of. I told you the products should be added to our products table, right? So I'll run a query to see. So there are 3 products now. So 3 products have been added. How do we know that it's working? We can run the query again and see if the number of products have increased. You see now it's 6. We try again. It's 8. So it will keep increasing and increasing. So next we run Debezium. But before we run Debezium is supposed to send out changes to RabbitMQ, right?
Less than a minute now.
To RabbitMQ. So now it is supposed to send it to this queue. This queue currently has 0 messages. So if it works, the number of messages in this queue should increase as well. So let me run Debezium. Yeah, we give it some time and monitor this. Yeah, it should go up. Yeah, so you see 17 messages now. It has captured these changes from our database. And lastly, now if we run our downstream component, the other app, it should receive these changes in real time.
Time up.
Yeah, this is the last component. Yeah, so the changes have been received. Yeah, and that's it for me.
Awesome. Thank you. Please. I would have loved us to take 1 or 2 questions for him, but your time is up already. So.